There, now, okay, great. So I have to admit this time was a little bit of a shock to have 20 degrees temperature difference between Sweden and Stuttgart, but I survived. All right, so I'd like to talk about some work we have been doing on modeling superconductivity in magic angle twisted bilayer graphene, and especially trying to understand if the atomic scale modulations that are present because of the moiré pattern is important for superconductivity. No, it's just not working. Oh, well, let's do this one. Oh, yes, there we go. Great. All right, so what I'm going to try to convince you today, or I'm going to show you, is a self-consistent and atomically resolved modeling of the superconducting state in magic angle twisted bilayer graphene, and show you that you then very easily get moiré and both moiré and atomic scale nematicity. It's a D-wave nematic state. Despite being a D-wave state, it's actually fully gapped, and we also see nematic signatures in the density of states. So that's what I'm going to show you today. But before I get started, let me just acknowledge the people who actually did all the hard work. So most of the code and the calculation was done by my former PhD student, Thomas Lötman, here with the help of another former student, Johan Schmidt, and the postdoc, Farbos Hiskar. And of course, none of this work would have been possible without a number of funding sources. So since this is the first talk on twisted bilayer graphene, just to give you a super short introduction to the topic. So what happens is that we take two layers of graphene and we rotate them a little bit. And then you develop this supercell moiré pattern where you see you can either have the two lattices fully overlapping with each other and you create so-called AA regions, or where they don't fully overlap and you get this AB or BA regions in between. What is very fascinating is that you have, if you have very small angles around 1 degree, you can develop very flat bands in this system. It's illustrated here. So here is this flat band region around 0. It's in a total 4 spin degenerate band in the non-interacting state. And this bands being very flat creates very high peaks in the density of states, which you see here. It has very pronounced Van Hoff singularities too. There is a Dirac point here in the middle, but overall they contain several of these sharp peaks. If you look at how this looks in the real space, it's also very modulated. Well, you can maybe imagine that because this lattice structure is very modulated. And what's happened is that there's moiré bands here that live predominantly with electrons in the A regions. So you get very high peaks of density of states in the A regions. Whereas in the AB regions, you have very few electrons. So why are we interested in more fundamental about flat bands? Well, the flat bands, as I show you, they create very divergence density of states. And as we know, if you have even weak interactions, very easy to get ordering. So fundamentally, this is a way to get ordering in a system which doesn't have maybe very strong interaction, but nonetheless, the interactions become strong because the kinetic energy is so low. So just give you two very simple examples. To get magnetism according to the Stoner criteria, you need the density of states times the Hubbard U to be bigger than 1. And even if the U is very small, if you crank up your density of states, you're of course going to fulfill this very quickly, even in a weakly interacting system. Similar with superconductivity, the transition temperature will in the simplest BCS theory depend also on the density of states. So we can have very weak interaction and we still get a finite TC just because the density of states are so big. There, maybe? Is that better? Okay, great. So this is, of course, why these peaks in the density of states coming up with the magic angle and twisted bilayer graphene could be very interesting for, well, all sorts of ordering. And that is also what's seen experimentally. So this is the first data from a few years ago showing as you tune the filling of these moiré bands. So this is the tuning of the moiré bands. And here is the temperature. So there's superconducting domes developing in the structure here, separated by what was labeled as a not insulating state in between. Later experiments. Let's see. No. Okay. Oh. Ooh. Sorry. My computer asked me if I wanted to shut it down. No, I don't. Let's see. Now it works again. All right. So this is some other summary of some other data. It's actually a few years ago, but nonetheless, this shows that you can get the superconducting domes appearing essentially across the band filling of these 4 moiré bands and often interspersed with insulating states. There is a lot of work on this, of course. I'm not going to go through all of it, but there is seems to be some similarities with cuprates, some similarities with conventional superconductor. Here I'm going to focus a little bit more on the similarities with the cuprates. You're going to see in a while why. So first of all, we have strong coupling compared to the kinetic energy. There's both superconducting domes and this multi insulating phase. There seem to be my computer.
It is disconnected?
Yeah, the Zoom is disconnected. Sorry. Yeah. Yes. All right, so. Okay. It's very bizarre. Share. Okay, great. Sorry about that. I don't know if my computer's not liking this or not. Anyways, it seems to be a pseudo gap phase, some strength metal, or at least linear in temperature resistivity also found in the system. So there is some similarities with the cuprate superconductors. So how do we model this? Well, we want to do it on the atomic lattice to really see if we can capture this atomic scale modulations. We know exist in the density of states, that also shows up in the superconducting state. So we model the interlayer pair. The interlayer kinetic energy is just essentially graphene, right, with nearest neighbor hopping, and then some chemical potential we can tune, so we can tune the filling of the moiré bands. The interlayer hopping is also what's become standard. It's a hopping between the 2 layers within some exponential decay, where you take the bond angle into account. And what's notable is you need to around 250 interlayer bonds per atom to actually capture the band structure accurately. But if you do that, we get this band structure. So here are the 4 isolated flat bands. They're not exactly flat if you zoom in enough on them, but they clearly have very clear Van Hoff singularities in the structure coming from the flat parts of the spectrum. And here you see that it's really, if you zoom out on this energy scale here, you see that it's a very high density of states sitting right there. This figure here is just showing that this is really tied to the twist angle. So this is a peak of the Van Hoff singularity, depending on which angle we have. It's really coming here. This is why it's sort of a magic angle where the density of states really goes up. This is just this model's charge density in the full moiré cell. So we have a very high charge density here at the AA region, where it's a very little charge density. Well, it's not 0, but it's much smaller in the AB and BA region. Formally, we have D3 symmetry, but it's approximately D6 symmetry. Yeah, now we go fast. Okay, this was the second. Sorry about that. I don't know. I have no idea what's causing the problem. Wait, so that was the kinetic band structure. I don't think there's much argument about that. Then the question is, how do we introduce the interaction in graphene, especially if you want to model a superconducting state? Well, we can go back to what's done in graphene, and there we have a nearest neighbor hopping is around 2.5 eV that sets the kinetic energy. And then from ab initio calculation, the on-site repulsion U has been estimated to be around 6 to 10 eV, so it's actually quite high if you compare to the nearest neighbor hopping. So we're in some sort of intermediate coupling regime, which of course makes it hard to solve to see can we get superconductivity from this. We can go back even further. further back in history and take a look at what is graphene really coming from. Well, graphene is an infinite sheet of benzene rings, right? So these are p-pi bonded planar organic molecules. And to get the chemistry of these organic molecules correctly, you want to favor nearest neighbor spin singlet bonds over polar configuration. And this gives you good estimates of cohesive energies, easy bond distance, and various exciton energy differences. This is nothing else than Pauline's resonance valence bonds idea that explains these aromatic molecules. So we're going to use this, and in physics language, it's nothing else than favoring this spin singlet bond configuration. And here is where this similarity with the cuprates come into, because if you put this interaction on a square lattice and you solve for superconductivity, well, you get the effective D-wave state that the cuprates have. So we're going to solve self-consistently for then the kinetic energy and this interaction. So that means I'm going to see what superconducting state I get on the twisted bilayer graphene, that if I solve it on the square lattice would give me the D-wave superconductivity of the cuprates. So the self-consistent solution is nothing else than on every single bond I want to calculate the order parameters, just expectation value of this spin singlet operator, and that I can do at any temperature, including T equal to 0. We're also going to extract the TC from our linear gap equation. So here we just have, so close to TC, we have small order parameters, so we can extract a stability matrix that connects the diverse order parameters. And we can simply see when this stability matrix have eigenvalue 1, we get TC. So these two gives the same. If you solve the self-consistent equation T equal to TC, you get this. So they, of course, they're not, well, two different equations, but they give the same answer. Before going to the result, just run through what sort of symmetries we would expect from this sort of pairing. So we're going to have pairing then on nearest neighbor bonds like this. And this is a 3-fold or 6-fold lattice. So we have 3 different possibilities. We can either have what we would call an extended S wave. So it's isotropic in space, follow the symmetry group of normal state. And that has the order parameter that are the same on each bond. Then you can have 2 different D-wave solutions. One that has an order parameter that is twice as big on this, and then changes sign on the other 2 bonds here. You take this conversion and you Fourier transform it, you get the D plus D x squared minus y squared state, as you see here. The other D wave has no order parameter on this bond, and 1 here and minus 1 here, and Fourier transform that, you get the dx xy squared solution. These are the only possible states you can have if you do the group theory analysis of this order parameter. And in graphene, it turns out if you solve this on a single layer honeycomb lattice, these 2 are degenerate. They belong to the same 2-dimensional reducer representation. And you get the chiral combination D plus ID happening very stable on the honeycomb lattice. And that is in real space, nothing else than the 3 cubic roots of 1. If I again would have taken this and solved it on a square lattice, I would get just one of the D-wave solutions, because these 2 solutions do not belong to the same irreducible representation, so you just get one of them. But we want to take this and solve it now at the magic angle and twisted bilayer graphene. The problem is that it's around 11,000 atoms, and we want to calculate the order parameter self-consistently on every single nearest neighbor bond, and we want to do it also preferably at low temperature. This is too big to do exact normalization, so we need to do something else. So what we do is we expand the Fermi operator. We create the Fermi operator. Essentially, it's just the Green's function and anomalous Green's function. From the anomalous Green's function, we can get these expectation values that we need for the self-consistent criteria. And you can calculate this Fermi operator by various expansions. You might have heard or worked with a Chebyshev expansion, for example, or Chebyshev polynomials. The problem with those are that they can be hard to work at very low temperature, because they create ringing if you have a sharp Fermi-Dirac function. So instead, what we do is we do a rational pole expansion. So we expand this Fermi operator in tabulated rational poles, and they are very sharp instead. So they're very good at low temperature. And also a side benefit is actually that it's very easy to take derivatives of this. So we have easy access to all response functions, including the linear TC equation. So in the end of the day, this is what we need to do. This expectation value that we need to calculate superconductivity is essentially creating a set of linear equations where we have to solve for this P vector here. And we can solve it in parallel, and the matrix is sparse. It's a good numerical setup. One thing that surprised us a little bit is that we actually needed a dense K-point sampling to reach convergence. It's a big cells, and we still had to have a lot of K-points to reach convergence. So here are the results. So here we are plotting TC, the critical temperatures, as function of the coupling strength, the strength of my of this effective attraction I have in my model. And the leading order is here in green. You see we need even to get TCs around 2 to 5 Kelvin, we need very small coupling strength. And this is because of the flat band. We have a lot of density of states, especially if you compare to graphene that's undoped. Undoped graphene, the coupling strength is up here. So it's a huge benefit to be in this twisted bilayer graphene regime. Moreover, this state here is twofold degenerate, belong to the E reducible representation. And if you plot the two solutions, they look like this. So for now, ignore the arrows. I'm coming back to the arrows, but concentrate on the color scale. So I call the solution delta X and delta Y. And you see that delta X is nematic. It was a Bragg's rotation symmetry in this direction. It's elongated here. And the delta Y is elongated in this direction. And clearly they also concentrated here in the A regions, which is natural because that's where the density of states peaks are. So these are degenerated TC. The question is what happens if I go below TC? Presumably we will pick one specific configuration. So it's higher order terms that kick in and pick one. So what we do is that we just write the most general combination of them with two angles, theta and phi, and simply see what the energy landscape looked like. So this is an energy landscape at t equals 0 as function of these two angles, theta and phi. And the lowest energy is found actually here on the real axis. So I don't have any complex value here. So if you plot that, we get this energy. So now plotted the energy landscape on this axis here, as function of theta here. And you see it oscillates, and you have 3 minima. So the minima up here is actually just a sign difference, so those are not unique. So we have a threefold degenerate ground state. The order parameter is always real. So this is a nematic ground state. And interestingly, if you take the chiral combination, so you insist that you should have a pi half here, you end up in this point here. It is the worst energy of the system. And the chiral one is also the only one that will restore full symmetry of your order parameter. So the full symmetric order parameter turns out to actually have the highest energy in the system. What's even, well, what was surprising for us is that this nematic state, this real value, the order parameters actually have a full gap. So here is the density of states plotted in these 3 points. So here in blue is the ground state, and you see it has a full gap. The worst nematic state is sort of, if you see it up here instead, the gap disappears. So then you understand why this is worse than this state. And the chiral state is gap, but it has a smaller gap than the nematic state. So what we end up with here is a nematic state with a full gap. And that should be compared to if you have done this on the single honeycomb lattice, then you would have had a gapped chiral D-wave state. And on the square lattice, you would have had nodal D-wave states. So in some way, this is a little bit of a combination. I have a real order parameter, so it's not chiral, but I have a full gap still. So this was the overall scale, nematicity on the moiré scale. We can also look what the order parameter look locally. So now we take the order parameter from every single bond and we decompose it into the form factors. And there's 2 different D-wave form factors and also an S-wave, but the S-wave is essential 0, so I'm not including it here. And we can write a vector field based on this coefficient here. So I get get an angle tau, and I can write a vector field just based on that tau to see how my d wave state went. And that is exactly what those arrows were that I told you to ignore before. So now you can focus on the arrows. So the arrows describe which d wave configuration I pick in my unit cell. So here you picked the dx squared minus y squared, but up here when the arrow is sort of in the vertical direction, you pick the dxy squared. So clearly in the regions with high delta, where you have this red regions here, you have essentially dx squared minus y squared symmetry, but then it actually rotates through your moiré cell and you get these vortices. So these are not superconducting vortices, it's a vortex in the nematic vector that decides which d wave state we have. So we have to change d wave state depending on where we sit in the moiré cell. Another, for us, little surprising thing is also there is a rigid pi shift between the two layers. So if you looked at the vector fields for the order parameter in the top layer and the bottom layer, you see that it changed direction. That means that the order parameter have changed sign between the two layers. And if you look at the condensation energy as function of this interface, interlay phase difference, so now we force a different phase difference between the interlayer, and we simply look at what is the energy. We see it's clearly is lowest when we have this pi change. That's also why we self-consistently converge to that solution. But any other phase difference essentially very quickly gets rid of your gap in the system. So then you can imagine why that is less favorable. And even if you don't have any phase difference, you even have a positive condensation energy. Well, here that sign means that you don't even have a superconducting state. That state is worse than the normal state. So it's very important to have this pi shift to get superconductivity. I should note, if you just do this in Bilayer graphene, you force a phase difference, you don't develop a gap in the system. So this gap, if you get here, really comes because we have the moiré structure, not just because you have two layers. So finally, let me just show you that it's actually possible to measure. So if you were to find this state, can measure it. And yes, we actually found even signatures in the density of states in the superconducting state. So I'm going to show you plots moving in various directions across the unit cell, so sort of try to prove this directional dependence. So here shows those for each of these plots here. So distance versus energy. And one should note that you, for example, if you look here, you see that it's developed some quite a big difference. And if you look at the normal state, not all of these are actually the same in the normal state, but number 1 and 3, number 2 and 4 are actually equivalent in the normal state, whereas in the superconducting state, the density of states pick up this nematicity in the order parameter. And it is actually a little subtle. This is the density of state on one sublattice, because if you were to sum over both sublattice sites A and B, this effect is not there. There's a sublattice difference. So here I plot the difference between density of states on the A sublattice and the B sublattice, and you see as we crank this vector from X and up to Y, we get more and more sublattice differences. So if you can have atomic resolution, you should be able to see this nematic D-wave, the nematic signatures in the density of states. So with that, let me just summarize what I've been talking about. I've been trying to show you data on superconductivity, magnetic angle, bilayer graphene, that is self-consistent and atomic scale. And we will use the realistic electron-electron interactions is similar to what you would have in the cuprates. Nonetheless, what we find here is a very different state. We have both moiré and atomic scale nematicity. It's a D-wave state, but it changes dramatically through the unit cell, both in terms of where it peaks and also in terms of which D-wave solution we pick up. It's also a fully gapped nematic D-wave state. So it's a D-wave state that have a real order parameter, but we still have a full gap. There's also an interlayer pi shift between the two layers, and there are signatures of this state in the density of state. So with that, I thank you for your attention.